and thanks everybody for coming. This is a great audience. I gave this talk, I don't know, 2-3 weeks ago at the University of Chicago Data Sciences Institute. So I wrote it for that, but this is a bit of a different audience, but I've given it since then to an online seminar. So we'll see how it goes. I'm hoping that it won't be the case that the ecology part is too obvious and the statistics is too difficult or too obscure, and that would suck. But let's see how it goes. I'll try to adapt it as we go. So I'll just start right off the bat. This is collaborative work. It started with me and Emilio Berti, who's at IDIV in Leipzig in Germany, coming up with an idea of doing this, and that has evolved over a couple of years. And now we have a grant that we're doing it, and Town and Jorge did give us lots of advice, and Benjamin has helped with technical things, and Angel, my postdoc, who's here, is heavily involved. He spends all of his time doing this stuff. So he's leading the day-to-day right now. And I should also say right off the bat, we've developed some statistical approaches to species distribution modeling, which help start to answer certain questions, which I'll describe. But it's also a tool, and we really want to get people to use this. So if anyone is at any level, student or postdoc or PI or whatever, and you see this and you think, oh, that would be fun to try on my species that I'm interested in, then I'd love to talk to you about it, because we have an R package that's pretty mature and usable by now, and so you could try these things out. And it's species distribution modeling is what we're doing. So it's the kind of thing that you could do to whatever species you want. And there's so many species with data available that, we can't do it ourselves. We can't even start. So if anyone wants to get involved, that's great. So now that I've prefaced all that stuff, I'll just give an introduction to what is the problem that we're talking about. Probably for an ecological audience like you all, this is all quite familiar, but let's just go through it quickly. The question is basically, why is a species found where it is on Earth? So here's just a random example, the northern maned sloth. And this is where it's found according to the IUCN. Why is it there and not like a little bit further this way, or up here, or down here, or somewhere else entirely? Here's another example. You can get amazing data about birds because people love them and they're visible. So here's another range map, which this one's from eBird. And in this case, it's divided seasonally. So this is common firecrest. Purple is year-round areas. Other colors are different seasons that it's found in those places. So why doesn't it, for instance, occupy more of Morocco? It can obviously get there. Why doesn't it go farther? So that's the question that a common reason for this. I mean, there's many reasons, but a kind of commonly addressed approach that looks at one of the common reasons is sort of climatic limits, like maybe there's something over here that it's a little bit drier or something that it likes. And so there's a climatic reason or an environmental reason why that constrains its range. Or maybe it doesn't go up here because it starts to get too cold in the winter or something. Okay, so, and the related question is, where will a species later be found under climate change? We know climate change is happening, things getting warmer, other changes taking place. And so in 50 years or 100 years under an altered climate, if a species can move, many of them are moving. I'll say something about they are moving their distributional ranges. And so can we say something about where it will be later? So this is generally, I mean, it's quite well documented that in a sort of general sense, species that can move are moving poleward, like northern in the northern hemisphere, southward in the southern hemisphere, or upward in elevation. There's a lot of exceptions and caveats and so on. Like, for instance, this is a figure from a paper of Malin Pinsky, where he showed species, different distributions of different fish species moving, not always northward, not always poleward, because of, well, as it turned out, the species were moving in the direction and at the speed that the climate was changing in that local area, which wasn't necessarily always poleward. So in some places, it's the other way. And in some places, for instance, where you can't move northward, the species go deeper instead, where it's colder. So here's a common approach. This is just a summary of the philosophy of species distribution modeling generally, and then I'll get to what we're doing that's different in a minute. Very commonly available are occurrence records for species. So you can go to something like GBIF and download records, basically sightings of your species. And those come from all sorts of places. GBIF aggregates many things. So if you have iNat on your iNaturalist on your phone, you can report having sighted a species. And if it gets verified, it gets eventually taken up into GBIF as a sighting for your species. So you'll get, for instance, this is a kangaroo rat, and these are sightings of the thing. And then you'll also download some data, which is, let's say, temperature and precipitation layers. And this is the key part that I think is the shortcoming of SDMs that we're trying to address. These are traditionally static layers that represent average, like average summer temperature over a 30-year period, or average winter over a 30-year period, average spring precipitation over a 30-year period. Whatever layer is that you think might constrain your species' geographic range, traditionally, people have just used the average value of it. And then you have a statistical model that tries to figure out what values of this are best aligned to constrain this. And that statistical model produces a suitability map, which you adjust the parameters of this model to make that map agree as closely as possible with those points. And then, having trained the model, you can then stick your future climate layers through it and predict the future range. So that's SDMs, and I mentioned GBIF. The species occurrence data are widely available. Occurrence records available for many thousands of species on there. GBIF and come from lots of other places as well. And these are detections of the species. They usually don't have, I mean, it's much less common to have a data set that has non-detections. So that'll just be a record that someone went there and saw it. And they'll maybe give you a time and some other information. They typically won't have information on someone went there and looked for it and didn't see it, which is a limitation of most SDMs, and it's not something I'm going to address. So typically what people do is through all sorts of tricks and best practices, they assume non-detections, usually in as reasonable way as they can, and then they use those as though they were non-detections. So here's this is the main shortcoming that our project is trying to address, and that's that 30-year average that I was talking about. So 30-year averages of climate variables are what's used. That's what I was saying before. So 30-year average climate is assumed to be what constrains where a species can live when you fit one of these traditional SDMs. But I want to just do a real oversimplified thought experiment to get the idea across. I think I made some arithmetic errors on here, but let's go past that. Let's consider two polar bear populations. And polar bears, I'm going to assume, which is a little bit true, but not completely true, that what polar bears do is they ambush, they hunt seals from ice. They wait for the seals to come, and then they hunt them, and then they eat them. And they really need that in the spring, especially because the pups are coming out from hibernation. And so they're reliant on decent springtime sea ice. They're actually more adaptable than that, but let's ignore that for a moment. And let's imagine location number one is -5 degrees C every spring, all the time. It's always -5 degrees C. So the spring ice the ice is always pretty good. Good enough, at least, right? And let's imagine another location which alternates between 10 degrees colder than -5 and 10 degrees warmer than -5 in alternating years, right? So the average is still -5, but it's variable. What that means is half the years it's above freezing and there's no sea ice, or the sea ice melts really quickly. And if you've got, I don't know how a polar bear population is going to persist over the long term if half of the years the main thing it needs for hunting is absent, right? So it's got the same, those two imagined locations have the same average conditions in the spring, but one of them is not going to be not as good of a place for polar bear populations to exist over the longer term. So that's what we're trying to get at. This interannual variability must be important. It has to be important. And so how do we try to take that into account? The second shortcoming of SDMs, and sort of the sub-theme of the rest of the talk, is that these SDMs don't consider population processes at all, really. They just are phenomenological models, at least the traditional ones are, right? They just take the detections and then they sort of fit a statistical model relating these climate layers with the detections. And they don't think at all about what the actual population processes are that convert the climate, the environmental fluctuations, and the environmental conditions to whether or not a species can live there. And of course, there's a lot there. It's like a whole field of ecology called population dynamics, right? And so that's all just modeled away, like abstracted away, which is a reasonable thing to do to start with. Don't get me wrong, I've made plenty of sweeping assumptions in models, but let's see if we can relax that. So we want to add some demography or population dynamics and actually think about how demography mediates the relationship between the environment and the occurrence versus absence stuff. Okay, so this, just to restate the main question, how does climate variability constrain species ranges? How can we try to infer that from the commonly available data? And by commonly available data, what I mean is like detection records from GBIF and climate data, which you can get oodles of anywhere. And the secondary goal, just to restate, can we help bring population demographic processes into SDM approaches? And I want to do it without making them require unavailable data. So you can make really complex data models, and there have been some papers that have done it, and they're good and inspiring papers, but they are really hard to work with. They take 40 days for their statistic model to converge, or they require data which just are not usually available. So I'm trying to stay away from that. And so this was all suggested in 2009 by Bob Holt, who I think most people in here know. Okay, so just a quick note on shortcomings. When I identify shortcomings of SDMs, I don't really intend to criticize them too harshly. If you love SDMs, you can go right on loving SDMs. I'm not trying to, like, I can see why people would do these things in SDMs. A lot of sins are covered by the idea that you've got a conservation problem and it's urgent and you got to do something. So an SDM is what you come up with. And it sucks, but it's the best you got, right? And so you go forward with it. And so we're just trying to build on that. Okay, so I want to give a couple pieces of motivation for why we should think about variability. Like, why? Why not just stick with the usual way of doing it? And one of them is just that variability is increasing. So variability, it's climate change, as you all know, is not just warming, it's also other changes, including increased variability, increased extremes. So this is an example. I gave this talk in Chicago. This example actually covers a large area centered on Chicago. It's a paper from 2004 where they looked at variability increasing. And so this is number of heat waves, number and duration of heat waves in Chicago now and in the future, basically just showing there's going to be more and longer heat waves in Chicago. They mentioned Chicago because it was at the middle of the phenomenon they were studying, but that phenomenon actually probably already spans all the way down to where we are. I'll show a plot of it here. Yeah, here we go. So this is the same paper, and this is the 500 hectopascal level anomalies. So that is like the level where a certain pressure occurs in the atmosphere. And when it's higher, it tends to indicate hotter. When it's lower, it tends to indicate colder. And so the top is 61 to 1990, and the bottom is 2080 to 2099 compared to this same baseline. So this is just showing the prediction of this paper that you're going to have more intense heat waves in this area in the future. So that's increased variability. You don't have to, that's one example. There's lots of papers talking about changes in variability of different climatic things. Here's another one. So that's why we should try to understand the role of variability in species ranges. One reason is because it must be important based on that polar bear logic. And another reason is that it's changing, so we should understand its impact. I'm going to skip this one. Okay, so let's give an example of how this is basically like a slightly beefed up version of the polar bear example, a little more rigorous, the next step towards the modeling that we're going to be doing. So it's another toy example, but it's got a little more quantitative meat on it than the polar bear example. So let's imagine a real simple population model. This is called the Lewontin-Cohen model. Population at time t+1 equals some random factor lambda t times population at time t. Lambda is the annual net growth rate. And we're going to assume that that random factor is a function of whatever the environmental factor is that's influencing the population. So maybe this is spring rainfall or something. And when the spring rainfall is big enough, the population can grow. When it's too low, it shrinks. When it's too high, it shrinks because it gets flooded out or something, right? So let's imagine this is time, this is that environment, and we've got two different locations represented by the two colors, red and blue, and they both have the same mean, which is this dashed line, but the blue one is less variable. So these error bars show the variation in each case. And if this function is given by this, so this sort of asymmetric bell curve-like thing is the relationship between the environment and the growth rate that we're imagining. And then let's say, it's pretty biologically reasonable to assume it's kind of shaped like this. And then these are the values from here. And if you pipe them through and get growth rates, these are the growth rates. And you can see the basic problem. If it's bigger variability, you tend to be in the shoulders more and less frequently in the middle. And so your growth rates tend to be lower and more. And you end up with a population that declines instead of growing through time. Stochastically, but as an expectation. So that's what we want to take into account. So this is, by the way, this Lewontin-Cohen model is the simplest model of stochastic demography. I guess the simplest model. It'd be hard to get any simpler than that. Stochastic demography is the underlying math of our approach, and it's a whole field, but it's also something, for instance, that gets applied, the IUCN. One of the ways that you can get a species red listed under the IUCN red list is to do a stochastic demographic analysis of it, population viability analysis, and show that it's got a probability of extinction over some threshold amount or a certain amount of time. So this stochastic demography that we're sort of building our framework around is an applied thing. There's other ways you can get a species red listed because a lot of times you don't have enough data to do a whole population viability analysis. Okay, so now I'm going to sketch the model, the way we approach this. And I think the best thing to start with when you frame a model is to say the kind of data that you're modeling, because that's really kind of crucial for the whole thing. So it's occurrence records from GBIF. So those would be these black points in here for this example species. And then assumed non-detection events. And I'll sweep that part under the rug, but there will be a series of best practices for saying that we're willing to assume that all these orange dots, someone went there and didn't see it. This red range is the IUCN range for this species, by the way, which is the IUCN ranges come from they ask an expert to draw a line on the map where they think the range is, and that's what they drew. So the model components are these. There's the population dynamical model, which is going to be that same Lewontin-Cohen model we just used, although we're in the process of elaborating that. But for now, it's the Lewontin-Cohen model. There's going to be a demographic response function, which gives the dependence of the demographic rates on the environment. So for the Lewontin-Cohen model, it's just the dependence of that lambda t on the environment. And it'll be that same bell-shaped curve, except for a more elaborate version of that. And then application of stochastic demography to give a measure, to convert that into a measure of population, let's say it's a stochastic growth rate, called the long-term stochastic growth rate, which I'll describe in a minute. And then a detection link which is a phenomenological link from this quantity from the stochastic demography and how it relates to how detectable the species would, and according to the model, be in that location. So let's go through and describe those different pieces, and then I'll bring it all together after that. So this is the population dynamical model. It's the same thing. For now, we're using this, which is really simple. I'm right now writing code to do a more elaborate version that takes into account stage structure and age structure, basically structuring the population. But for now, this is what we've got. Lewontin-Cohen model. It's assumed to apply in each location on the landscape. It's just that this lambda t, which is going to be determined, I'll describe in a minute, from the environment, is going to be determined from the environment in the location where you're applying it. So the demographic response function is I already wrote a picture of it in the toy example that I did. It's this function f that relates the environment to the net growth rate. Previously, I had written down just a univariate value of E right here, but it could be a vector because the net growth rate probably depends on more than one environmental variable. And it'll just be a function. So I'm going to describe the univariate version, and then I'll describe the multivariate version of it. But the univariate version is that thing I drew a picture of. It's a kind of an asymmetric bell curve. So if you're familiar with the PDF, probability density function of a normal distribution, this is that, but made asymmetric. So it has two branches. So it can have like kind of a different standard deviation parameter one way or the other. That's all we're doing here. And then it also can model things like this that are saturating just by choosing one of those two standard deviation parameters to be huge. So it doesn't fall really on one side. There's also a multivariate version of this. These are pictures of the bivariate version. So just think of the multivariate standard normal PDF or normal PDF, and then make it asymmetric in any direction. So this is like a normal PDF. This it's wider that way than it is these ways, and you can also rotate it. So we've got a function that takes that flexibility into account, and the model parameters can be adjusted according to whatever is going to end up fitting the data best in the end. Okay, so now we've got our population dynamical model. We've got how the growth rates in that model depend on the environment. All these things are contingent on model parameters, which are unknown and which will be fitted in the very end once we've constructed the whole thing. So now we're going to use this. This is the tool from stochastic demography. It's called the long-term stochastic growth rate. If you've done any stochastic demography, then you've heard of this because it's like the main quantity of stochastic demography. But if you haven't, that's fine, because I'm going to tell you basically what it means. In our model, it's this quantity. It's just the expected value of the log of the lambda t through time, which is pretty straightforward if you've got a bunch of lambda t values that you've calculated from the environmental time series, contingent on model parameters. You just have to log them and then take the mean. So given model parameters and an environmental time series in a location, you can use the demographic response function to get the lambda t's, these net growth rates, and then you can calculate really quickly through this formula, the long-term stochastic growth rate. So let me tell you what this long-term stochastic growth rate is. It's the growth rate of a median of an ensemble of populations. So if you took the model and you simulated it from the same place, same starting condition 1,000 times, some would grow faster than others, and you take the median of that trajectory and you work out its growth rate, like it will grow or shrink exponentially. And that growth rate, that's the long-term stochastic growth rate. So it's really just kind of the median growth rate of a median of a bunch of population simulations. I'm going to skip this technical definition of the same thing. So the model structure is you start with the environmental time series, you pipe them through this growth environment function. That's that asymmetric generalization of the normal distribution. And then you get lambda t time series. You calculate from those the long-term stochastic growth rate. And then long-term stochastic growth rate is a growth rate, right? If it's higher, what that means is that this population can grow in that place according to the model with its current parameters. And so it should be more detectable. I mean, because it's able to be there, right? And then if it's lower, it should be less detectable because like it's less likely to be there, right? So all we do is we put that long-term stochastic growth rate through a sigmoid function, which we call the detection link. Here's the standard. This is just the standard formula for this logistic function. So PD, and it has parameters as well, which are later fitted to the data. So PD is the maximum probability of detection. Like some species are just intrinsically less detectable than others. Even if they're thriving in a location, you might not see them when you go there. So we need a parameter for that. Right now it's pegged at 1, but it's an adjustable parameter. And then B and C. So C is the center. Like what is the stochastic growth, long-term stochastic growth rate? That's halfway in between undetectable and as detectable as the species ever gets. And B is how quickly the transition occurs. And given environmental time series in a location, you can get the lambda t, these net growth rates, for each year from the demographic response function. And then you can get the long-term stochastic growth rate for the location from those lambda t's. And then you can get the probability of detection from that sigmoid function. And all of that is contingent on the parameter. And then you can write down a likelihood function, which compares those predictions with your detections and assumed non-detections. That likelihood function is just like the logistic regression likelihood function, and then you can fit it. So this is the standard SDMs. Same picture that I had before, but like rearranged. And this is the new version. And I just want to point a few things out here. The standard SDM just takes a flat climate layer, one average map. And this takes like a time series worth of maps because at every location you have to feed the whole time series of environmental data in. And then the machinery of the model breaks down for each of the locations where you have a detection or an assumed absence. It extracts the time series of environment for that location. That's these. Pipes them through the model, the stuff I just described over the last few slides, and gets a probability of detection out. And then that's that map gets optimized for agreement with the occurrences, or the optimizations are adjusting the parameters of this. And this thing, which is the blow up of that, is the slides that I just went through. So you take the environmental time series, you stick them through this, which is contingent on parameters, you get growth time series, and you get population that either is shrinking or growing according to the current parameters of the model. And then that translates into these probabilities of detection. So it's similar in some ways from an SDM to an SDM. It is an SDM, but it uses time series instead of flat layers, and it has dynamics inside of it. It's simple dynamics, but it's still dynamics. And then having attained these probabilities of detection out this side, you can fit them with your occurrences and assumed non-detections using a likelihood function, which if you've ever looked at logistic regression, this probably looks familiar. If you haven't, don't worry about it, but it's the same basically likelihood function from this point as logistic regression. So now fitting the model, we've implemented both frequentist and Bayesian tools for doing it. The frequentist tools are more developed. That's the package that we could give you and you could just start using if you wanted to do it. And I'm sweeping a few things under the rug, but let's not worry about that. So now that's the model. I want to show you the application of it because I guess you didn't come to see that math. I just wanted to try to give you the idea of how it works. And now I want to show you some application for it. So I'm going to start by showing a simulated application because even though I know some of you might be groaning and actually wanting to see a real application, I think that's jumping the gun. Like you can't make a new statistic and not try it on simulated data first. If you do, you're really walking on thin ice. So let's do it for simulated data and make sure it works, and then use it on real data. So what do I mean by simulated data? I'm going to take the model, I'm going to use it to generate some data, like detections and pseudo-absences of a virtual species, and then I'm going to fit the model to those data and make sure that I recover the original parameters that I used in the model to generate the data. If I can't do that, then I've got no hope of inferring anything about real data, right? So we better do that first. So when I say simulated data, the simulated part is the occurrences and the detections and the non-detections of a virtual species. We'll use real climate data. So this is real climate data. So for an area over the Black Hills of South Dakota, rectangle, I think it's about 128 by 123 kilometers. We extracted 39 years worth of data. And the two variables we're using for this example are mean annual temperature and total annual precipitation. So time series of data at 1 kilometer resolution over an area of South Dakota. Here's the mean of this bio 1 is the temperature variable, and this bio 12 is the precip variable. This is the average across all the years, standard deviation across all the years, same for the precip. So then we took this model and we made up some parameters and we simulated it to generate detections and non-detections for the species. And here they are. So this is meant to be like what you get from GBIF. Like there's some species that lives in South Dakota, and people go out and every time they see it, they go, oh, great, I'm going to report it in INAT. And these are the data that come back. And then this is somebody who's willing to assume that they went to all these locations and looked for it and didn't see it. So it's detections and non-detections, pseudo non-detections. And so we fitted multiple models. We didn't just fit the model that we generated the data with, which had the model. So this model involves both of these variables influencing the range of the species. This is a species who is sensitive to both temperature and precip. And so both variables actually influence the generated data. And now we're going to fit three different models. The one that has both, the one that has just the temperature, and the one that has just the precip. And we're going to do a model selection exercise with AIC. And I'll skip the details, but the true model was the best supported one, which is a relief, right? And then you can do profile likelihoods, which is the way that you construct confidence intervals. And if your method is any good, then you should tend to get confidence intervals which contain the true parameter that you use to simulate the data with, right? And we did. So these profiles, where they hit the red line is the confidence intervals, and these are the different model parameters, and you can see it sits in there. And also you could take the actual demographic response function, remember that thing which tells you the relationship between the environment and the annual growth rate, and you can look at the true one and the inferred one and compare them and make sure they look about the same, and they do. So this is the inferred one, this is the true one. These black dots are just the environmental values for locations where the species was detected, superimposed. But the point is that the inferred structure of the model and the true original structure of the model look real similar. Inferred and actual probability of detection maps, agreed. So this was the true probability of detection or habitat suitability, and that's the inferred one, and they look pretty much the same. And then so what people usually do is they take some sort of habitat suitability map like we just showed and threshold it and just decide that we're going to call the species range everywhere where it's above a certain value, and outside the range is everywhere it's below a certain value. When you threshold it, they also look about the same with not a lot of difference. So we didn't just, that's an illustration. We did a more systematic simulation study. So when you do a simulation study to assess your new method, you can't just do it for one set of simulated data. You have to do it for lots of sets of simulated data under different conditions. So we did, that was what I just described was a stand-in for the real simulation study where we did that. But the point is that we did a big simulation study with lots of simulated data sets. And this sort of summarizes the whole thing. Depending on the number of detections, the number of GBIF records that you have, like simulated GBIF records in this case, the true probability of detection and the predicted probability of detection agree pretty well. And if you've got more than 200 presences, it agrees better than if you've got less than 200. So that was one simulation study that we did. Now that one is the so-called generating model, the model that we used to simulate the data from, was the same as the model that we fitted to the data, which is never the case in reality, right? Like whatever model any of us cooks up, it's not the model that nature used. It's some simplification or whatever. It might be completely wrong. So that's called the problem of model misspecification. So we wanted to simulate model misspecification. So we invented another model, which was not the same model that we were going to fit the data with. It had density dependence and some other features in it. And we simulated data from it, and then we fitted our model to that. Now we know that our model is misspecified. It's not the same as the generating model, but because we know in real life, that's always going to be the way it is. So we fitted to that to see how well our model did. And while we were at it, we fitted all these other, this is ours, all these other ones are standard SDM methods that are used all the time. And so this is the same format as this. True probability of detection, predicted probability of detection. And our model did pretty well. That's not it's really comparing it to these other models is not really the point, as none of these other models take into account variability, but we did this along the way. Okay, now for the real data and the real species. On one side of me, I kind of can see that maybe some people are bored by all these statistics. But on the other hand, like, you got to lay the foundation. You can't just jump in. All right, so let's go back to our original question of how variability constrains species ranges. And I should say we started to answer this. We've basically done it with 22, well, 10 or 22. You'll see why in a second. I'm saying two numbers. Example species. We haven't done it comprehensively. We haven't done it for one whole clade or even one whole genus. We just grabbed a bunch of species, which are diverse, and we tried it for them because they had good data and other characteristics that we liked. So for 22 example species, we fitted models with different combinations of several different temperature and precipitation variables because we didn't necessarily know which ones are going to be the ones that constrain the ranges of those species. We did a model selection exercise to figure out for each of these species which model is the best one to use from among the ones we considered. And then we judged the quality of fit of our best model. And we only kept the 10 species that it turned out we ended up with a pretty decent model. So we wouldn't, like if you just start with a species and some environmental variables, you have to admit the possibility that that something other than the environment constrains the range of the species, or that some environmental variable constrains the range of the species that you didn't consider in your, so you have to consider the possibility that none of your models is any good and throw those species out before you use the model to infer anything, right? So we did that, and that's why we have 10 species here when we started with 22 up here. And Angel right now is like, he's a great computer scientist, and he's beating the cluster to death, trying to fit thousands of species, as many as we can. So we've got this pipeline that he's been building. We do lots and lots of species, but for now, this is what we have. And then, having done this, we've got our 10 species. We then wanted to know what's the role of variability. Well, we can take our fitted model, and we can take all of our time series of the environment, and we can replace them all as nice wiggly time series with flat lines equal to the mean. Like we can decide what if in every location instead of the environment being what it actually was, fluctuating from year to year, it was just equal to the mean value the whole time in that place. So that's taking away the variability. Pipe those time series through the model and see how the predicted range of the species changes. So that's what we did. We could call these no variability ranges, like what the range of the species would be if it weren't for variability. Here's our 10 species. So we were just looking for some diversity. So here's some example results. Ranges were smaller with variability than without it. So when you took away variability, the ranges expanded, which I guess you might expect that to be generally the case. On average, they were 22% smaller with variability than without, and up to 45% for this glass lizard here. So these red areas the blue areas are the range of the species as estimated using our model from the GBIF data and our whole statistical framework. And then the red plus the blue is what the range would be if only that climate would stop varying around all over the place. So that's current climate. That's trying to get an idea of the role of variability in constraining species ranges. And I guess the headline answer, just let me finish my sentence. The headline answer is that it does, as you might expect, and it does it in a meaningful amount. Like it was possible a priori that instead of getting 22% and 45% here, we would have gotten like 2%, 3%. And then our answer would have been, well, you all can carry on with your same old SDMs that you've always been doing, right? Jim.
I was just distracted by that example because in that example, when you remove the variability, did you re-parameterize the fit with a constant environment or just take your parameters that you included the variability and remove the variability?
The second one, because that's what we want. So,
but on the other hand, if you could predict that the better model without the variability, the way they were doing beforehand, that would be informative too.
It would be, but it may not be extensible to futures.
Yeah, I agree with you that. Yeah.
All right. It'd be like being right for the wrong reasons, right?
I agree with that. That's what the entire premise is here, right? So go ahead.
Yeah.
Turn to that.
Okay, so we next wanted to seek to answer the question of how changes in variability under climate change might influence species ranges. So we went through a huge effort, which we ended up scrapping, to try to get plausible estimates of future mean and variability of climate indices. And like, it's damn near impossible. It's just impossible. You have to put in so much effort to evaluate. We gave up. We ended up doing what you could call sensitivities instead. So we basically said we want to calculate a derivative of the size of species range with respect to changes in the mean and changes in the variability of current climate. So it's a near-term thing. It's like if let's say mean temperature goes up by epsilon, how much does the range change? If the variability of temperature goes up by epsilon, the same epsilon, the standard deviation and mean have the same units. The standard deviation of temperature goes up by epsilon, how much does the range change? And can we compare those quantities? Because it could be a priori that the sensitivity to changes in variability is tiny compared to the sensitivity of changes in mean. And then we could say, well, it's okay, we don't have to worry about all this variability nonsense. Or it could be that they're comparable in size. So that's what I just said here written down and in slightly more technical language. But basically, it's two sensitivities. And here's our 10 species. These are sign sensitivities because that's what derivatives are. They're positive. They could be positive or negative. So the red is sensitivity to changes in the interannual standard deviation of temperature, whatever temperature variable was in the model. We just did temperature. And then the yellow is sensitivity to changes in the mean. So This corresponds to the effects of getting a tiny bit warmer. This corresponds to the effects of getting a tiny bit more variable. And you can see the bottom line message here is that it isn't the case that the red ones are tiny compared to the yellow ones. Sometimes they're smaller, sometimes they're bigger, but they're comparable size. Summary of results. Interannual climate variability seems to have a substantial role in constraining species ranges. Ranges appear to be similarly sensitive to potential future changes in both variability and mean temperature under climate change. So far, we're in the realm of what I like to call like what every ecological study in the history of the universe does. Does X matter? And the answer is always, yes, it matters, because in ecology, everything matters. So this is one of those studies. So so far, we're still in the realm of every single ecological study in the history of the universe. And now, but this is what I think, this is a methods component. But basically what we've got is a tool that we can use on species to try to study this. And we're expanding the tool to more elaborate models that don't just track the population. They track like juveniles and adults and allow for different sensitivities of juveniles and adults. There's the preprint. Also happy to talk about it. There's a lot of limitations. How much time do I have left? I'll say a few words about limitations. It's important to sort of acknowledge these things. I didn't address the pseudo-absence problem at all. It's still there. Density dependence. So this might seem to be a limitation, but I would argue that it's not. That's my argument, at least. Like, what constrains the range of a species? I think what it must be is, like, when the species gets knocked down in that location, can it bounce back? When it gets there, can it grow? The density part kicks in at higher densities, right? So I think their range is probably constrained more by what the dynamics at low densities. So I feel justified in ignoring density dependence in the model. We're ignoring complexities like Lee effects and stuff like that. Dispersal, we're basically ignoring. So we're assuming that dispersal, once a species gets there, has limited effects on whether a population can persist there, which is true for some species, but definitely not true for others. Like any metapopulation-like species that exists through a balance of colonization and extinction, this won't work for at all. And we can't figure out, I don't know of a mathematically and like computationally tractable way to put that in. You can always simulate everything, but then you get back into the realm of the studies that I mentioned back at the beginning of the talk, where it takes them 40 days for their model to converge. Because you can't just, the stochastic demography really speeds up the computation. Instead, we can calculate that long-term stochastic growth rate very quickly. If you have dispersal in your model, then you have no choice but to simulate your entire metapopulation many times and measure extinction risk in each place, contingent on model parameters, and then adjust your model parameters, repeat the entire exercise, and that's your way forward, which takes forever. But maybe like maybe that can be improved. Local adaptation, we haven't put that in. We're assuming the same response everywhere, the same relationship between the growth rate and the environment everywhere, which is obviously not the case. Like there are plenty of examples of species which are locally adapted and they have different temperature tolerances, let's say on the south end and the north end of their range. So we're ignoring that now. We do see a way to put it in, like a hierarchical modeling approach where we allow that growth environment function to vary geographically according to some other parameters which also have to be fitted. We just haven't done it yet. And thanks. And like I said, if anyone wants to talk more about this or try it out, then I'd be really happy to hear